Hmm. Correct. Hmm. Correct. So it's 6:05. Uh, I think I'll start because if we wait now, it will be late. So anyway, as usual, I'll give a brief recap of what was, uh, you know, what was covered in the last week. So basically, uh, like availability or exergy discussion was the important. One second, let me just check whether I'm on mute or not. No, I am not on mute, so this is fine. So I think video and audio are okay. So anyway, we'll start. So basically, since now you are aware of what is availability or exergy, there is a like very typical question which is asked in many interviews. What is like this is the question? What is thermodynamics? So when you will appear for any interview or something, so it's a very typical question when you say thermodynamics is my one of the favorite subject. They'll say what is thermodynamics. So one definition is that is usual one. The thermodynamics is a branch of science that deals with energy interaction between system and surrounding, and it goes like that. So that is very typical definition, and everyone will give that definition. But there is a very few people who will be trying it in a different way. And I also, when I was in my interview giving phase, I also tried to look for some another definition, because in interview you have a very small time to make an impression on the interviewer. So if someone asks you what is thermodynamics, you can just say that thermodynamics is a branch of science that studies or deals with three E's. So this is three E's. So basically, E for elephant, that type. First one is energy. So essentially, first law you can explain this way, that it is basically energy balance. So that is one E. Then you can say enthalpy. And yeah, the third one, since you already know, it is exergy. So some people will also like to include entropy here, and that's okay. But so basically, if you want to include entropy, what you can do is you just don't write energy. You start with enthalpy itself. Then you can go for entropy and then exergy. So this basically defines the way in which you study the thermodynamics at an undergrad level. So enthalpy essentially is a energy, or sort of, let's say if it's a open system, you associate the flow energy, kinetic energy, potential energy, and all sorts of things in. I mean, like overall, you do the energy balance. There, the enthalpy term comes. It is if it is a closed system, then it's not enthalpy; it's internal energy. So that's why I am giving you a choice. You can either say enthalpy or energy. Energy will be a safe choice. I would use energy. Then entropy, essentially the second law, the spontaneity law. So this is the quantity, and this defines quality. And these are like you can relate first law, second law to energy, entropy, that terms, and then this exergy, which is a very important concept, but it's a in undergrad many people are not uh, aware with this. So many people don't mention exergy in interviews and all, and many people fear about this exergy also. One second. Priyanka, can you see and hear me properly? Just once confirm it if you can.
Yes, sir.
Yeah, so I don't know when you joined, but what I was saying is since exergy has been discussed last week, so uh, if anyone asks you what is thermodynamics, you can define it in this way also now. You can say it's a branch of science which studies three E's, and those three E's are, you can say, energy, entropy, and exergy. So now we'll come to our discussion. Uh, so this will help you in interviews, is what I'm trying to say. Because if you give an average interview, you'll get average marks from the interview. So this is helpful for, let's say, if you are, I don't know what is happening with engineering services nowadays, but if you are going for such UPSC exams, apart from GATE, in GATE also for PSUs, you have to give interviews. So there you can use this trick. This may give you slight advantage, but you should be prepared. If you say this definition, you should be prepared for next question. So if anyone asks you what is exergy, because not many people will say exergy voluntarily, and if you say exergy voluntarily, you should be in a position to say what is exergy. It doesn't matter that you know exact definition or not. Even if you know more or less uh, practical utilization of this term, that is also fine. So anyway, what is exergy? If you want to define, I would say I'll not go into the book definition. That you can refer to any standard book, Pekenag, Moran Shapiro, Sontag, and many more are there. So you can get the actual definition or line by line. If you want to mug up, you can go there, but that won't help because you'll forget after some time. And anyway, so the thing is, exergy is actually a uh, hmm, a unit, I can say, not unit, a measure of uh, potential for doing work. So, for a given system. So basically, if it is a high exergy, or I can write the equivalent term is availability, but it's actually long to write, and exergy is easy because you have energy entropy. So something like that is exergy. So anyway, so these two terms are used interchangeably. They are same only, synonyms. So it is a measure of your system to like it's a measure of potential of your system for doing work or to do work. So first law tells you about the energy balance, but like we need second law to tell the spontaneous direction of that process or the cycle, whether it is a feasible device or process or not. That comes from the second law. And this exergy or availability, it comes into picture when you basically shift from reversible processes or reversible devices to practical devices. So basically, uh, if you have a reversible heat pump or something, you know, you are basically neglecting all the practicalities, the friction, the mixing, and all those things which bring the irreversibility in the process. So irreversibility can be due to two things. One is due to internal processes within the system, such as mixing or free expansion, something like that. And there is a irreversibility due to heat transfer, which is an external irreversibility, we say. So because of these irreversibilities, you you lose some potential to do work. So basically, if you not did not have these irreversibilities in your system, between your system and surroundings, then you could have achieved more output from your system, work output basically, which is what we generally desire in work producing work devices, and minimum work input in work consuming devices. Whereas if these are heat exchangers, uh, you desire that maximum amount of energy, energy, or the maximum amount of exergy or availability that is coming in with the hot stream, that should be given to the cold stream, and there should not be any irreversibilities in between. But there will be irreversibilities in practical systems because you can't avoid it. So that's where this exergy comes into picture. I'll not go into the philosophical argument because that will take a lot of time, and we don't have that much time. So basically, uh, what we do is I'll just write uh, some some things which will help you solving important problems. One is work reversible is actual work plus uh, work loss due to irreversibilities. And this we write it as T naught into S gen. What is the entropy that was generated when you have surroundings at T naught? And this is for work. I think it is work producing device like turbines. One thing that I've noticed is the problems that we mainly discuss for this week. They usually focused on work producing devices such as turbines. 1 second. Array. Uh, but if you have a work consuming device like compressor or pump, there your actual work, I'll write this way, for work consuming devices rather than device like compressor, etc. Uh, your actual work will be what was the reversible work required plus some additional work that you need to do additional to overcome irreversibilities. So basically, uh, in that case, and this will be formula remains same T naught S gen, but you have to provide this much more work in reality. You can't expect the same work input as reversible process. You have to do some additional work. So this part I thought was missing in the discussion this week because we mainly focused on turbines, but there are compressors, there are work consuming devices, or cycles which need work. So like heat pump or refrigerator. So there you have to give additional work. So you should remember this because based on this you define the second law efficiency as actual work. Okay, okay, I'll write this. I should have made two columns here, but anyway. So actual upon reversible, this will be true for turbines because there you actually get lesser work and you have to provide uh, like lesser work compared to the reversible work, and it will be just opposite for compressor. There you have to give uh, more actual work than the reversible. So basically that you should remember. And yeah, so this was the availability thing. Then what you do, you study it for open system and closed system. So for open systems, we generally define a availability function which was given by this symbol psi in the video lectures. So it is basically h plus v square by 2 plus gz minus t naught s. So this is the availability function. So if you are at inlet, you write psi I equal to hi plus vi square by 2 plus gz minus t naught s. Remember, this is always t naught wherever you are. And then one trick question will be, what is the availability when your system is at ambient conditions, so ambient temperature and pressure. So in that case, your psi 0 becomes h0 minus t0 s0. Because like when you say it reaches to the ambient, the velocity becomes 0, and you consider that system is at the datum from where the potential energy is measured. So that also becomes 0. So you have only these two terms in your system uh, is at equilibrium with the surroundings. So this is one. And then what you do uh, for maximum work, uh, you know, your system should return to the, like, the final state of your system should be ambient state. So that will give you maximum work done, and that condition will happen when you, uh, I mean, for example, let's say if you have open system like this, uh, there is some heat transfer from TH QH, and there is some heat rejection. Uh, so let's say T0. I'll take. I mean, it doesn't matter. You can say TL. Sorry, QL TH. This can be zero or non-zero. Okay, this is not a heat engine, so this is not necessary to be uh, non-zero always. This is a simple flow process, and these things can have opposite signs also. I mean, there need not to be always heat addition or heat rejection. So basically, there will be one stream with E, and there will be one stream with exit, and you may have some work output also. This thing can also happen, and this is your control volume. So this is a generic control volume. It will not resemble with any practical system, but these are all components that will be present at max. So we generally say work is a high grade energy. So you know there will be no availability destruction, no exergy destruction when work transfer is there. So basically, the idea is, if you have, let's say, potential of your system is, it can give you 100 joules of work output that can be completely used for another system, and to drive the another system. So there will be no loss if you have the output from your control volume in work, which is high grade energy. Basically, it is a focused form of energy. So high grade form of energy can be uh, kinetic energy, potential energy, those type of energies, which are, you know, they'll not degrade due to the molecular motion of the particles. Whereas if you consider heat, so if there is a, like, let's say this QL, generally we treat heat as a low grade energy because it's not a concentrated form of energy. So if you want to do some work using this heat, you'll have to first, focus it somewhere. So basically, for example, when you do combustion in IC engine, when you burn the fuel, you do MCV. CV is the calorific value of that fuel. So if you, let's say, burn M mass of fuel and CV is the calorific value, then you get MCV from MCV amount of Q. But that Q is not useful to you. You can't do anything with it. So what you do, you put a piston cylinder around it. Then that Q, because of this expansion of gas, the piston will be pushed in a reciprocating motion, and that is a form of concentrated or focused, because you now have control over that motion, because it's always be linear. Then you put crank and shaft assembly after piston, and you get a circular or the torque at the wheel. Basically, I mean, wherever you want, you get the torque. So that torque is high grade energy, but the heat released due to combustion is a low grade energy. So that's why there will be losses. So basically, you cannot convert 100% of low grade energy into useful work. So that is again, if you want to discuss, you can go back to the Kelvin Planck and those thermodynamic statements also. So basically, uh, there will be non-zero exergy destruction when there is a low grade of low grade of energy interaction. So yeah, these are the terms: low grade, high grade, exergy or no exergy destruction. So anyway, in general, what we are going to use is, uh, so let's say if you have a steady state steady flow process, SSF. So what happens there? You'll have reversible work done. These formula I'm just writing because the derivation was done in the class. So if you have some heat interaction, like in this control volume that I've drawn, so this much is heat coming into your system. So you can do this much of reversible work with it if you put some, let's say, heat engine in between. And this much of heat is leaving your system. This is for this control volume, which is shown on my screen. Okay, so uh, don't confuse. In class, there was some different type of control volume was taken. If you do this way, it will be this much work you'll lose basically because of QL, Q dot L. And we'll assume this is a maximum work condition. So this your T will be equal to the ambient, which is subscript 0 basically. I'll not write 0 here. Maybe some of you get confused that this is 0 or something, but no, this is ambient. So maximum reversible work done when your exit state is ambient. So you'll have m dot I, and you can just write psi I here minus m dot E, and you can just write psi 0 here. And the psi definition is this. So please remember that this psi 0 will have 0 velocity and 0 potential energy. So only H0 minus T naught S0 will be there. So this will be for your maximum work done, reversible work done for your control volume. And if you want actual work, what you can do is first law of energy balance. So basically, what is your energy incoming to the system? It is QH plus m dot IHI, and what is leaving is QL, Q dot will be there, and m dot E H0, since your HE is H0 plus work done actual. So using first law, you'll calculate actual work, and for reversible work, you have this formula. So this is for SSSF, and we'll typically deal with this type of problems here. And next part is if it is a control mass system. So here, only thing that you need to remember is your availability function. It will be defined with the different symbol psi. No, this is phi. The earlier one was psi. And it will be U minus T naught S plus P naught V. So basically what happens when you have a control mass system, uh, the boundary, the boundary of your system is a movable boundary. In this control volume system, your system boundary is a fixed region in the space. But in control mass system, let's say this piston cylinder assembly we studied a number of times during the first initial part of course. So this is your piston, there will be some spring or something, and this is your ambient P0, and this is your control mass or your system uh, control mass CM, and then you do some heat addition or something like that you do, and you study the behavior of your system. But what happens if you add heat and the same amount of heat is not taken out from your system? Eventually internal energy of your system will increase, and it will cause the expansion if this is air or any gas. So then your system boundary moves, and it does work against surroundings, which is at P0. So therefore you need to have this much additional potential to do work. So that's why this plus P naught V term comes. So yeah, so for that, if you want to write, you can just say, let's say W dot reversible. We'll assume steady state also here. I mean, you can just say WH 1 minus T0. Let's say this is WH at TH. So T0 is ambient temperature. So this will be work potential due to heat QH, Q dot H. Then uh, let's say you'll have some, if there is uh, you know there will be not W, because then it won't be a mass system. And let's say if your initial mass was some m1, then you had initial availability as m2, phi1 minus final uh, m2 phi2. But this is a control mass system, so your m1 will be equal to m2 from mass balance. So you can just write m1, and there will be some potential from your uh, system boundary movement. So this is how it should look. And again, your actual work will be reversible minus irreversibilities basically. So this is T naught SN. This is for work producing device, like this piston cylinder, which can produce work. So this is the basic thing. And yeah, one more thing. If you have, we'll take one problem of this also, heat exchangers. I'll explain there in that problem, but here the definition of second law efficiency is change in exergy of cold fluid divided by change in exergy of hot fluid. I had this doubt for a long time when when I was preparing for exams, because the tutor who taught me, they only told me second law efficiency for these work related devices. But in heat exchanger, you actually don't have any work interaction, and you generally assume it as adiabatic, so you don't have heat interaction also. So there, how will you define the second law of efficiency? Uh, Personally, I had this doubt for a long time. Eventually, it was cleared, but I'll give this to you that in case of heat exchanger, any non-work producing or non-work consuming device, you just take the exergy desire, like whatever you wanted to do, how much exergy was received at that application and how much exergy you applied for that application. So basically, that's how you define second law efficiency. Now we'll start the problem. We are already late. So example one. In the last class, Narendra was here, but today he is not. But he gave a suggestion to include, if I can describe the problem rather than just solving it. So basically, there is a very common template when you see any competitive exam questions. Uh, this question is asked many times in GATE also, 2-3 times. So what I'll do is, this question is basically, I'll just read out a question. It can be asked in different forms. Okay?
Sir, hello, sir. Sir, I am present. I am present. I
Okay,
joined
okay.
late today.
Acha, acha. Yeah, so sorry, I could see only two names here. Your name is Rasika, is it?
Yeah, sir. Today I joined with a different NID.
Okay, okay. Yeah, then fine. So basically, what this is a very common question. It can be asked in different ways. So I'll just read one question. There is a heat reservoir which is at 900 Kelvin, and it is in contact with the ambient, which is at 300 Kelvin. So it's a hot reservoir basically, and for a small, like whatever duration of time that that reservoir was with the surroundings, let's say it did some work. I mean, you put some heat engine between and it did work. So there was some sort of availability associated with this process. Now what you do, you reduce the temperature of your hot source, heat source. So instead of 900 Kelvin, you use a heat source of 600 Kelvin, let's say, and your ambient is still at 300 Kelvin, and you do the work. So intuitively, by this time you should guess that uh, if the heat is available with which you can do work, uh, and if you have a choice, let's say I am giving you heat at, let's say, 600 Kelvin, and I am giving you heat at 900 Kelvin. So basically, which heat source will you choose? And your objective is to maximize the work output. So you can relate this type of philosophical argument to the availability thing, and I'll give you some. So basically, case one, your TH is, let's say, 900 Kelvin, and T0 is 300 Kelvin, typical 300 Kelvin. And case 2, TH is 600 Kelvin, and T0 is same. You are using same ambient conditions. So now, and you know, so what happens in this case? And you are supplying, like the implicit assumption is that same amount of QH, let's say, same amount of heat is supplied to do work. So if you have such condition that you have, let's say, 100 joule of energy, and you supply it at 900 Kelvin or 600 Kelvin, which is better? So this question is asked many times. So what you can do is, you'll basically imagine this better if you plot it on TS plot. Uh, so basically, by now you should know that area under the TS plot for any process gives the heat interaction. So if I am doing, let's say this is my 900 Kelvin, and I am adding some QH. Uh, I'll give you some sort of value just to be, do better calculations. So what should we take? We'll say 18,000 joule. So 18 kilojoule. You are adding 18 kilojoule at 900 Kelvin. So what will be the area by this process? Uh, so if this heat addition is done, and you're surrounding it at 0 Kelvin, then only this whole area will be the heat interaction, right? But you are having surrounding at, let's say, some 300 Kelvin. This point, this is your T0, this is your TH1, just for the sake of notation. So this much area, let me highlight it by some other color. Sorry. 1 second. So this much area is your, net. Like if you add 18 kilojoule, this much is the area covered by that thing, that much heat. So now in the second case, what you do, you reduce your TH. So this 600 Kelvin is your TH2. Now in this case, see, now the area is half, but you are adding same heat. So you need to increase this area to have same amount of heat, like same amount of area under the curve. I hope you are getting my point. It was like this. And you are adding same heat here, which is 18 kilojoule. But the heat temperature or the inlet temperature of your heat is lower. So now this becomes your area under the curve, or the area under the this thing. I mean, it should not be. I mean, let's not confuse ourselves. It should be like this, something like this. This is just a notation. So you see what is happening here is as you reduce your temperature of heat source, the entropy associated with that process is almost doubling. So initially this much entropy increase was there because of heat addition, and now this much, which is like because of our values, it is almost double. So as you know, the entropy generation is not good. I mean, in your system, it will eventually, because it will increase irreversibility, right? We take T dot S gen. So if entropy increases, irreversibility increases, and maximum work output potential decreases. So how much it got decreased by? So if you draw, like, I mean, 1 second. So basically, this area down here, I'll use this type of shading here. This area, which is which represents your loss of availability. So now your question will be, how did you achieve this? So I can just write it this way. What is your loss of exergy? Initially, how much it was? QH into 1 minus T naught upon TH1, and in say second case, it is same amount of heat, 1 minus T naught upon TH2. So if you simplify, there will be QH term here, T naught term here, and you'll have 1 by TH2 here minus 1 by TH1. So now you know this is positive, this is positive. So your sign of your, like whether it's loss or gain, will be defined by this term. And you know TH2 is less than TH1 because it is 600, that is 900. Therefore 1 by TH2 will be greater than 1 by TH1. Therefore 1 by TH2 minus 1 by TH1 will be greater than 0. So this quantity is positive. So that means it is a loss. You are losing amount of some amount of heat. And if you want to do it in a graph, this area represents that part. This much amount of heat this much amount of availability you lost. So this question is asked multiple times in GATE, multiple times in ESE. Recently, one sort of variation was asked, that there is a heat transfer across, heat conduction across a wall, which is at, let's say, 900 Kelvin, and the another temperature is at 300 Kelvin, and it's a purely conduction problem. So, and thermal conductivity, is not a function of temperature, so linear drop you'll get. So this type of question was there, I think, in 2014, 2015. It was 2 marks question, set 3. You can check the exact language there. But I'm giving you a brief here that this same argument which we did with QH1, QH2, this can be asked in this way, that and this is basically your ambient. It was mentioned that your ambient is at, let's say, 300 Kelvin, and the heat source is at 900 Kelvin. Some furnace, this can be boiler or furnace, anything which is at higher temperature, and there is a steel plate. So there will be heat conduction, and it was asked that assume no heat generation within this wall. This was given in the question. And what is the irreversibility due to heat transfer? So in that question also, if you follow this argument, you'll get the answer. It will be T naught. So basically, they just want the irreversibility. So irreversibility, if you want, you can just do T naught S gen, and T naught into S gen in this case will be what was the heat transfer divided by the into 1 by this TL minus 1 by TH. I hope I am not doing some calculating or writing error. But anyway, so this is how you calculate. So it is not a only thermodynamics related problem. It can be applied to anything where heat flows. It can be applied to power plant, anything. So this is a very, sorry for spending more time on this, but this is a very commonly asked problem. You should be aware of this. Now we'll go to the next thing. So I'll take one heat exchanger problem. I don't know whether you have uh, done it or not. Uh, uh, Before going there, do you know what is the parallel? Actually, parallel is not a 100% correct term generally, or you can call it co-flow heat exchanger. HX is heat exchanger. I am using this shorthand notation here. Versus what is counterflow heat exchanger. So if you are aware with these terms, that is good. If you're not, it's basically as the name suggests, in heat exchanger you have one cold fluid, one hot fluid. So if they flow in the same direction, this is hot fluid, this is cold, that is co-flow or parallel flow. And if they flow in opposite direction, they are counterflow. Which arrangement is better, which is not, that is a part of heat transfer course. But I'll just give you answer. It is counterflow because here your outlet temperature of cold fluid can go above the outlet temperature of hot fluid. So that's why you have a better heat transfer, a more amount of heat transfer. That is a general hand waving kind of explanation. But in heat transfer course, you'll learn more about this. But generally, it is better counterflow. So why I'm telling you this here is whenever you see question in thermodynamics course and nothing is mentioned, whether it's a parallel or counterflow, just draw it as a counterflow. If it is clearly mentioned that it's a parallel flow, then it's a different thing. If not, just draw it as a counterflow. So we'll take one example. I'll read you example first because I tried to get the screenshot or image of this question, but doing this in a live class, it's time consuming actually. So sorry for that, but I'll read it out. There is a heat exchanger. It's not mentioned which type of heat exchanger it is, and it's a basically boiler, constant pressure boiler. And so if you know what does boiler do, it's basically uh, it will heat cold water using some hot fluid. Hot fluid can be anything. It can be just product of combustion of fuel, or it can be some heat exchanger also. You can use some recovery from some other hot component also. So that can be oil also, hot oil. So we'll not bother about that. We'll just think there is one stream which is cold water, and there is another steam which is hot gas. So it's a combustion based boiler. And so basically I'll draw this, I'll draw it out while reading it. So it's a heat exchanger. You might have already solved this problem in Abhik's class. So I'm not bothered about the exact numerical solution or algebraic sum. I'll just give you a key points which you should not forget. So we'll draw it as a counterflow because that makes our life easy, because you'll see here hot gas, this is the hot gas. Let's say this is 1 and this is 2, and cold is 3 and 4. So this is cold water. I'll try to give as much information as possible in the question here, since I'm not giving you exact question. So for hot gas, m dot hot is 2 kg per second. Oh, my bad. It's not m dot hot. Actually, this is for cold. 1 second. For cold water, m dot cold is 2 kg per second. It is entering at 80 degrees Celsius and leaves at 400 degrees Celsius. And for hot water, only for hot gas, only temperatures are mentioned. So you'll have T1, which is 1200 Kelvin. If you convert it into degrees Celsius, what will it be? 1200 minus 273, so 927 degrees Celsius, and it exits the boiler at 900 Kelvin, which is 900 minus 273, 627 degrees Celsius. So here, one important thing to note is your water is getting heated to 400 degrees Celsius, and your steam is leaving at, or your hot gas is leaving at 627. So both arrangement can work. Counterflow heat exchanger can also work, and parallel heat exchanger can also work in this case. But if this T4 would have been, let's say, 700 degrees Celsius, then only counterflow will work, because in counterflow only you can go beyond 627 degrees Celsius. So I hope that is clear. So now this thing, I'll just write exact question, because that is the least that I can do here. To find, first is total rate of irreversibility in the process. This is first, and second law efficiency they have asked. So the objective of taking this problem is this only. How do you calculate second law efficiency? I have told you briefly, but we'll just sort of glance through it. So now we all know the rate of irreversibility is T naught into S gen. So here one more thing is, generally if it is not given in the question, you assume the heat exchanger to be insulated. But if it is not, then what? So first let's solve this problem using insulated heat exchanger. So in that case, whatever energy is coming in from the hot gas is going to the cold water. So by first law, you have m dot h c or cp of h, or whatever it is, specific heat capacity of h, in T2 minus T1. This much it lost, and it should be, if you are writing equality in between, it should be T1 minus T2, and that will be gained by the cold fluid. So cold fluid will be T4 minus T3. So here, what all you know all the temperatures given, and CH and CP. For water, you should know this, 4.186 kilojoule per kg Kelvin. For hot gas, it is not mentioned in the question what is the CH. So either you can assume it as 1, treat it as air or related to air, because in combustion also more or less it will be air only. Some sort of CO2 composition will change. So you can do that, or you can go to a, if it is given in question, or if you have table for that gas, you can directly calculate enthalpy difference. This problem was solved calculating enthalpy difference. So I am assuming they had enthalpy values given in the question. So you can do this both way. The main point of solving this problem is not the focus on your problem solving skills. So values may change slightly, that is fine. So from here, what will you get? M dot H, because in some kg per second, because that was unknown, right? Only M dot C was given. So that comes out to be 16.99 kg per second. So now you have everything. Now the question is total rate of irreversibility in the process. So here, this is a steady state operation, right? So total rate of irreversibility will be irreversibility in minus irreversibility out, right? So this is a steady state. So whatever is coming in and whatever is going out, the difference of those two will be, you know, the total rate of irreversibility. So how do you calculate that? uh, so who is bringing the irreversibility here? So basically, this is because of air. Sorry, not air, hot gas. They are using hot gas here. And this is because of water. I mean, this is a loose description. So basically, ideally, what is, I'll not confuse you. Uh, so irreversibility is coming in at two places, point 1 and point 3, and it is going out at 2 and 4. So basically, this will be 1 plus 3, and this is minus 2 plus 4. I hope this is clear. So this you can write 1 minus 2 and minus 4 minus 3. I'm just doing reshuffling of terms because this way you can solve the problem. So 1 minus 2 is basically decrease in availability of the air, and 4 minus 3 is increase in the availability of water. So their difference is the net rate of irreversibility. So now how will you calculate this? So we'll take the help of these availability function. So this will be m dot hot into psi1 minus psi2 minus m dot cold into psi4 minus psi3. And what is the formula for psi? As I said earlier, it is v square by 2 plus gz minus t naught into s. Here we neglect kinetic energy and potential energy terms because heat exchanger, they are not of that great consequence. So basically your psi is h minus t naught s here. So now if you want psi1 minus psi2, this will become m dot h h1 minus h2, and there will be t naught. I'm skipping one step here, but I think you'll get it if you just write it. And the second term will become like this only, m dot c h4 minus h3 minus t naught s4 minus s3. So now this enthalpy is, right, because you know temperature or you have some data in tables. Now what about S4 and S3? So basically this is a water. So this will become Cp ln T4 by T3, right? Because there is no pressure and all this. Whereas for hot gas, S1 minus S2 will be Cp ln T1 by T2 minus R ln Q1 by T2, P1 by P2. But here it is not given that the pressure of the hot gas is changing between inlet and exit. Maybe the flow length is not that much. So this term goes to 0, ln log of 1. So here also you have Cp ln T2 by T1, T1 by T2 here. So if you do all this calculation and you get the total rate of irreversibility, it should be coming around. I am not doing the calculation. I am hoping you are able to do this. 2138 kilowatts. That is okay. This is a typical flow for problems in this area. What you do, you apply first law to get some sort of unknown. It will be, in some cases, the mass flow rate will be unknown. In some cases, the heat transfer or the work done by the system will be unknown. So you'll find one unknown from the first law. That is a typically what it is in this type of problem. It is there. So you apply first law, you get that unknown. Now you have all the unknowns. Then they'll ask you what is the availability. So for that you need to get the help of availability functions. So this was an open system. That's why we get Psi1, Psi2. If it's a closed system, you'll get Phi1, Phi2. So you apply relevant formula for Psi1 and Psi2, and you apply, properly. There will be some delta S terms because Psi is H minus T dot S, right? So there will be an entropy terms here. So you apply correct relation for that depending on whether it's a solid or liquid or gas or ideal gas or whatever it is, air. And then you take a difference, and that will be your rate of irreversibility. And second law efficiency, which is the main part here. I mean, uh, maybe you already know, but I'm just still highlighting this. In this case, what is your desired output in terms of uh, your performance of your heat exchanger considering the reversibilities? So you want maximum exergy to go to the cold fluid and minimum irreversibilities to be there, right? But that won't happen. So here your this will be your uh, you know oh, 1 second, it is 4, right? For water it is 4, yeah. So m dot c into psi 4 minus psi 3. Some people call it psi also. I'm calling it psi, so it's just a pronunciation. And whatever exergy you put in this case. So if you do this way, you should get 0.489, but this value is not that important. I just wanted to convey that this is how you calculate second law efficiency for heat exchangers. For turbines and all, you do work actual by work reversible, right? So there you can imagine easily, but for heat exchanger it's tricky. Now my question is, note, what if this heat exchanger is not insulated? So this type of variation can also be asked in the exam. So here we solve the problem assuming Q equal to 0, right? But in reality, Q may not be 0. There may be some Q. So how will you solve this problem? So for this problem to solve, uh, and how will it affect your second law efficiency formula? These are two important questions. So see, if there is a heat loss, either it will be given or you can use first law to calculate it. So that part is easy. But what will happen to your second law efficiency? Whether there will be change in this formula, like should I add, let's say, plus Q here. I mean, this is loss, okay? Heat loss from the heat exchanger. Or should I add this term at the bottom? So what should I do? So this type of confusion is, it should happen in your brain if you are studying properly. But my answer is, I mean, the correct answer should be uh, the efficiency formula remains the same. Because what happens if there is a heat loss, your outlet temperature of water, which was 400 degrees Celsius in this case, it will not be 400 degrees Celsius. If there is a heat loss, it will be, let's say, some 380 degrees Celsius, something like that. So where, even if there is a heat loss, and if you don't consider it in the second law efficiency formula, it is actually implied. It is implicitly considered there because your T4 depends on your Q loss from first law. And if Q loss is more, your T4 will be lower. And if your T4 is lower, then this numerator term, which is psi4 minus psi3, that will be lower. So your second law efficiency is lower. So even if there is heat loss, you can use the same formula. So it will essentially affect your psi4. So that is the one point that I wanted to convey. So yeah, that is about the heat exchangers. Since we have some time, we started late. So what we'll do, this turbine and all I'm not taking, okay, because professor has also taken many problems on turbine, and you can also do on your own. So one more interesting problem, which is not that challenging for computation, but it is one important observation you can draw from it is I this problem might have been already discussed by Abhik, but if you're not there, uh, I'll read out the problem first. A 1 kg of copper, 1 kg of copper block is at 350 degrees Celsius, and it is suddenly dropped in 10 kg of oil bath, which is at ambient temperature of 20 degrees Celsius. And this oil bath is in a container which is properly insulated, so there is no heat loss. And for this copper block and oil bath system, first question is asked, what is the final temperature of your system? And second question is, what is the change in availability of the system? So these two questions are there. I'll just draw a simple schematic here. This is a simpler question. I will not say it's a tough question to visualize or anything, and that's good for us because you'll realize one important observation at the end. So this is your oil, and this whole setup is, I mean, I'm showing some air here, but it can be oil also. Let's not confuse. This is oil, so everything is oil. And there is no heat loss, so it is 0. So for copper block, T1 or T initial was 350 degrees Celsius, and Cp of copper is given, or C only. C copper is 0.42 kilojoule per kg Kelvin or kg degree Celsius, both are fine. And mass of the copper block is 1 kg. So this data is given for copper. For oil, initial temperature was ambient temperature only, which is 20 degrees Celsius. Mass of oil is 10 kg, and Cp of C of oil, specific heat capacity is 1.8 kilojoule per kg Kelvin. And you need to find, I'll write the exact sentence here, final uniform temperature of copper plus oil system. This is the first part. Second part is change in availability of copper plus oil system. So I hope the first part is not that difficult to solve. It's a basic application of first law of thermodynamics or energy balance. But you can properly write it in this way. This is your control volume, the whole thing. I mean, you can say control volume, control mass. This is fine, but better to go with our usual thing, control mass. This is our control mass. because there is no mass interaction with the surrounding. So this is control mass system. Then you apply first law to the control mass. So what is it? Q122 is delta U or U2 minus U1 plus W122. I hope this is, this is what we have done multiple times, so there should not be any doubt here. Here this term is 0, there is no heat loss, so there is no work done also from your control mass. So basically U1 is equal to U2, and what is U1? M of copper C T initial of copper plus M of oil C of oil into T initial was T0, and finally they are at some uniform temperature T, let's say Tf. In that case, M dot Cu CCU plus M dot oil C oil into Tf. I hope this is not confusing for you. This is quite straightforward. If you do this calculation, because you know everything here, you should get the final temperature as, I mean, if you put the values in degree Celsius, then you'll get answer in degrees. If you put it in Kelvin, you'll get in Kelvin. I will advise, because I made this mistake in one of the classes, put everything in Kelvin, so you'll not get errors anywhere. So if you put Ti, T0 in Kelvin, you'll get Tf in Kelvin as this much. So this is first part. Now second part, which is the interest topic of interest for us. Now it is asking what is the change in availability of your system. So basically change is final minus initial, right? So now what is your final availability of your system? You have copper and oil which are at Tf. So how will you write it? You can write it. See, wherever there is irreversibility, you have to take help of availability functions. Since this is a control mass system, you have to take help of psi function, which is U minus T naught S plus P naught V. Here the system boundary is not moving at all, right? So there is no P naught V work done here. So this term goes to 0, so our life becomes easier in this problem. But if it is, let's say, piston cylinder assembly, then there is a P naught V term also. So when, like, keep in mind. So there, finally you have some mass of copper, which is at phi. I'll write F. Okay, and some mass of oil, which is also at phi F. I mean, these phi F are not same. Okay, so phi F, I'll just write phi F for copper, and this is phi F for oil. So these are not same values. Don't make that mistake. And what was initially some mass of copper at initial availability for copper, and there was some mass of oil which was at some initial availability for oil. I hope this is fine. Now if you rearrange these terms, because you can take mass of copper common, right? So if you rearrange, what you'll get, mass of copper and then final availability function of, I'll not write copper here because it's confusing. I'll just write this way. So whatever was change in availability of copper, final minus initial, multiplied with the mass. This is, we are defining it as per kg basis. So we multiply mass again. And then there will be another minus, mass of oil, psi of oil final minus psi of oil initial for oil. So I am just doing reshuffling of terms, which I did earlier also. Here also I did the same thing only. This 1324, 122, 1443. Same thing you are doing here, and you are getting this type of expression. and this is easier expression to deal. Okay, you'll see why. I mean, again, this is UF minus UI minus T0 SF minus SI for copper, and similarly you can write this term and expand. And these are liquid and solid, so this SF delta SF formula becomes CPL and TF by TI for both, and this is internal energy change, which is basically specific heat of copper minus delta TF TI. So essentially you have all these values. So I'm not going into the solving part. What I wanted to tell you is this only. So if you consider these two terms, first for copper and second for oil, and if you solve everything, you'll get these values: minus 45.71 plus 1.69. So this first term, MCU 5, 5F minus 5I, is 45.71, and second term is this one, plus 1.69. So this is the key observation that you should do. I mean, you can take the total and this is minus 44. This is fine. I mean, uh, this is uh, this is just an algebra. But here you see, when your copper block was at 350 degrees Celsius and it was quenched at by using oil, which was at 20 degrees Celsius, its availability, you know, the decrease in its availability function is minus 45.7, so minus 46 times, whereas increase in the availability of oil is only 1.7 times. So that's why their sum is minus 44. So basically this gives you a idea about the extent of exergy destruction in this process. So see, this process, when you quench something, it's highly irreversible process, right? You cannot get back the system to its initial state without doing any effect on the surrounding, right? So the thing is, this can be one exercise. I'll leave it up to you. Assume that initial temperature of copper block was 500 degrees Celsius, not 350. And if you assume this as 500 degrees Celsius and repeat this calculation, finally you will get this value. This minus 45 value will be very, like, it will be around minus 60 or something, which will be higher than this value because now we have destroyed more exergy. When copper is at 500 degrees Celsius, it has more potential for giving useful work output, but you did not utilize that and you just quenched it. So there, if the temperature is initial temperature of copper block is 500 degrees Celsius instead of 350, you are destructing more exergy. So in that case, this minus 45 will be something like minus 60 or something. Whereas this oil term will be hardly around 2, 3. So one hand you are destructing larger exergy destruction. Sorry, this is destruction and very smaller exergy upgradation. So see, oil's exergy is increased by 1.69. You can take the unit as kilojoule here. But the exergy of copper block is destroyed by minus 46 kilojoule, almost 20 times. So this is the physical insight that you should develop now. See, calculations you can do. That is not a, I mean, that is required for the competitive exams. So that is not a part you should neglect. But parallel to that or alongside, when you solve problem, you should develop such understanding also, that you are destroying more exergy in one component, and that is resulting in very low exergy increase in the other oil. So that is not a good process uh, as far as thermodynamics is considered. You are basically losing more potential which you could have used for a useful work. So this is how it is. And second law efficiency is not defined for such systems, but if you want to loosely define second law efficiency here, what will it be? It will be, what was the increase in the exergy of oil divided by what was the total exergy input. So that will be coming from copper block only. So it will be something like this, and if you see, it will be around 2-3%. So which is very inefficient process. But I mean, this is not an actual formula. Okay, so don't blindly uh, uh, trust this one. Second law efficiency is defined for work producing, work consuming, and heat exchangers. But you can define it in a loose sense for another systems as well, just to get an idea how much exergy is destroyed. So here you see second law efficiency is only 2%. I mean, exact value, if you want, I can give you, but 1.69 divided by 45.71, it is 3.7% to be exact. So let's say 3.7%. See, in heat exchanger, it was 49% roughly. Here it is only 3%. So that's not a good uh, device as far as potential to do work from this system is considered. But Apple, like this system is not for doing any work. This is a quenching system, and it has some other applications. So don't think that this is a bad system or anything. For its purpose, it may be good, but from thermodynamics point of view, it is not an efficient system as far as exergy upgradation of oil is considered. So, so I think we'll stop now. I hope I have given you some sort of see this exergy process. Sorry, exergy thing is acha. Priyanka, you have raised your hand. You can ask your doubt.
Um, Hello, sir.
Yes, yes, continue.
Regarding the problem just now, what you did, if
Mm.
like you said about the physical significance of the negative value, if the
Mm.
change in the um, availability of the system was zero, it means it is 100% efficient.
Yeah, because whatever availability was coming in, you are utilizing all the availability to do either work or to increase availability of some other component. So if you are able to do it without any without any loss of availability, so that will be having 100% second law efficiency.
If it was positive number, then
Uh, we'll take some values. So let's say I am giving 100 joule of available energy, and then what is your question?
no, like if the instead of minus 44, if it was plus 44 kilojoule.
Mhm. When will it be plus? See, if you diagnose these terms, uh, what is happening is the reason why it is negative is coming from this phi f minus phi I, right, for copper, because
Yeah.
mass of copper is positive, so that leave that part. So this negativity is coming from two parts. One is this UF minus UI term, and another is T naught into SF minus SI term. So the final temperature of copper is lower than the initial temperature. So this specific heat into delta T, that term is negative. And uh, SF minus SI will be positive. One second. Cp ln TF by T. It will be negative, right? So, I mean, am I making sense? But one second, I'll just write it out. This was the change in availability for copper block, right?
No, no, not for this problem I'm asking. Generally, I asked, like, if it is
Acha.
positive, then is it like impossible?
Not really. Somewhere it has to be negative, right? Take this example of heat exchanger. Uh, it can be positive. Don't say that it will be negative always. For example, see in this heat exchanger, for your cold water stream, the availability change was 4 minus 3, right? I mean, m dot of water into psi4 minus psi3, right? This term.
Yes.
So that term will be positive. So you have increased the availability or exergy of your cold water. But it is not same as how much your exergy is decreased for hot gas. If it is same, then it is 100% second law efficiency, which is not a feasible process. Practically, that cannot happen. But it can be positive. The term that you are asking, uh, it need not to be negative always. It can be positive, and one example can be this problem that we solved for a heat exchanger.
Okay.
Is it? Did it make any sense, or are you still confused?
No. I understood.
Yeah. See, this availability concept is a tricky one. I have not, I mean, forgive me, but I have not gone into this turbine and all in this class because I hope many problems have been already done on that. This heat exchanger is a tricky concept. Uh, you please go through that slowly. Here we had time constraint. You can ask if any doubts are there next class also, no issues. But availability is a tricky concept. It took me a lot of time to grasp it. I don't know whether I know it completely by now. I don't think so. But at least whatever required is for this course, I think I can guide you. Uh, but for heat exchanger, it's tricky. Don't mug up the formula. It won't help. You should go through this process and find the values. One more question before we close. This is a philosophical question. We say energy of your system will be, let's say we are considering an isolated system. It doesn't have any heat interaction or mass interaction with the surroundings. Okay, it's an isolated system. So for an isolated system, the energy of the isolated system, will it be constant, will it increase, will it decrease? You have to answer this one.
Constant.
Okay, then entropy of an isolated system, uh, will it be constant, will it decrease, or will it increase? Any guesses? Uh, so let's say we studied that second law, right, which is a spontaneous law of spontaneity, basically. So if you have an isolated system, its entropy can remain constant or it can increase. It will never decrease. So that is the key thing that you should remember. So that I was expecting this answer, but let's say now you know that entropy can be constant. If everything in that isolated system is reversible, it will remain constant. If not, then there will be some dissipation and there will be entropy generation. So you'll have either 0 or greater than 0 entropy for an isolated system. Now the question is, which is relevant to this discussion, if you have an isolated system, its availability will remain constant, will it decrease or will it increase with time, let's say. I mean, you observe that system after some distant time. What will happen to its availability? What can happen? Uh, did you understand my question?
It will decrease.
Can it remain constant?
It may remain constant.
In which condition will it remain constant?
If the temperature remains same.
Nope. If it is, uh, it's an incomplete answer. You should say if the internal processes that are taking place in that system are reversible. because you know the reversibility is a function of temperature and pressure. So if it's a solid or liquid, you can say if the temperature is constant, the entropy is constant and availability is constant. But what if it's a gas? So gas entropy can, like, it's a function of two variables, which is temperature and pressure. So instead of going into that complication, you should just say if all the processes which are taking place inside that isolated system, if they are reversible, then the entropy generation is zero and then the availability destruction is zero. So it will be less than or equal to zero, basically, the availability change. So I hope that is clear. Is it clear, Priyanka?
Yes, sir. It's somewhat clear. I have to think about it again.
Yeah, just think about an isolated system in which, let's say, air is there, which is at certain temperature and pressure, and you do some sort of process where you keep the temperature of that air constant, but you reduce or increase the pressure. So, I mean, it's difficult to imagine because it's an isolated system, but yeah. So anyway, the answer is, you can think about it. If you still have some doubt, we will discuss later. But the answer is, if everything is reversible in that isolated system, both internal, external, whatever it is, it's an isolated system, so there won't be any external interaction, so it will be internal only. So everything internally reversible, so entropy generation zero and exergy destruction is also zero. So anyway, I'll just write one liner. You can remember it for gate or anything. For isolated system, change in energy. This delta is change, okay? Change in energy is zero. Its energy remains constant. Change in entropy, it can be greater than or equal to zero. And change in exergy, it can be less than or equal to zero. So you can remember it this way also. This may help you in some competitive exams. So yeah. Uh, 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 and the equality holds when the when the internal processes, or I could just say are the processes within the system are reversible. So this is one note you can remember. Okay, please ponder upon these topics that we discussed. These are slightly tedious concepts. If you have anything, we can discuss later. And for now, we can stop here. I think it's already 7:30. So should we stop? Anything from Narendra? Today he is very quiet. I think he's left also. Anyway, so shall we stop, Priyanka? Anything?
No, sir. Nothing, so.
Okay, that assignment, last assignment, did you have any difficulties or any problem with the solution, anything like that?
No, last assignment was fine.
Okay, okay. I think Narendra is not responding. Maybe he's busy. So we'll stop now. Okay?
Yes.
Okay, okay. Have a good night then. Bye. We'll meet next Tuesday.
Thank you, sir.
Yeah, bye. So now I have to stop presenting. I'll stop recording also. Yes.